Okay, so this video is the last part, day 4, if you will, of section 3.2. It's going to deal with some printouts. Um, and so when we say printouts, like in class, we use calculators to do a lot of our calculations for us, right? In the real world, when you get into college, if you take a statistics class, there are computer software that we would use. So you won't really use a graphing calculator. We use a graphing calculator because, for your AP test, you're not going to have a computer in front of you. So they design the class around using a graphing calculator. But real statisticians probably are not using that. They're going to go to some computer software. And so we'll look at a printout of a particular piece of software, and you'll need to be able to look at it and know how to pull certain information off of that printout. And then we'll talk about the limitations and some other issues that we need to sort of tie up and dealing with linear regression. All right, so this is a computer printout of something called the Minitab. So Minitab is a software that you can use to do statistical analysis of data. There's other ones as well. I know that when I was in college, we used something called SPSS, but here we're going to be using Minitab. So you have to be able to figure out and understand what these different things are. Okay. So they give us all kinds of information on this printout. It gives us the slope. So let me point to it here. The slope is this thing here. All right. The y-intercept, or what we call A, is the thing up above it. So these two numbers together allow us to write the equation of the best fit line. So B and A. Okay. The things we talked about last video, the standard deviation of the residuals is here. I suspect this is the forward data because that 5,740 sounds really familiar. We just talked about that last video. The standard deviation of the residuals for the F-150 pickup trucks. I suspect that's the case there. And then here is the r squared. It says r squared, right? That is the coefficient of determination. It always ends up spitting out this adjusted r squared. Just ignore that. That's not something we use or talk about. The rest of these columns will come into play more as we get into future chapters. Chapters like 7 and on. And we'll revisit this. But for now, all we're interested in is these things. All right, so a couple other pieces of information. So it says the predictor, right? And then it says constant, and it says miles driven. So this listed right here is always the explanatory variable. So if you remember from the F-150 example, we were using the number of miles on the truck to predict the price that the truck sold for. So the explanatory or X variable is always listed here. And so you can think of it sort of as like the coefficient of this variable. Well, that's the slope, right? So it's always plus or minus B and then X. So this is the coefficient of this variable, and so what those two things intersect. So this is always the slope, and then the constant, that's like the coefficient of the constant. Well, mathematically, we just call that the constant, right? So that's what this is here, and that's the A. That is the y-intercept. All right, let's look at an example. All right, so here we have printout. Minitab printout, and it tells us that this is relating the height, someone's height versus their foot length. So we're using either their height to predict their foot length, or we're using their foot length to predict their height. How do we know which one is which? And so remember this here, foot length, that is the explanatory or X variable. Okay, so now having said that, use Minitab printout, write the equation of the best fit or least squares regression line. So y hat equals what? Pause the video, write it out. All right, so instead of y hat, we might just think about using height hat, right? Because height is the y variable, is the response variable. And so if you said y hat and then 103.41 plus 2.7469x, if we used x and y, we would have to explain what the x and y are. So it's sometimes nicer, instead of using a y hat, use the response variable height, hat, and then put foot length in instead of just the x. Because if you use x and you use y in the equations, then you have to then explain what the x and what the y hat stand for. All right, so find s for me. Well, I mean, it's pretty obvious. It's right here, right? Yes, that is the s. And then find r squared. Okay, again, that's pretty obvious. It's this one. Again, you're not using the adjusted. Ignore that. The r squared of 48.6%. Okay, and so now can you tell me what r is? So we know r squared. Can you tell me what r is? It's really that simple. You just take the square root of it. Now the question is, if I take, r squared is always positive. When I take the square root of it, your calculator will always give you a positive value. How do you know that it's positive 0.697? How do you know it's not negative? Because your calculator is never going to give you a negative when you take the square root of a positive number. So how do we know if r squared is positive or negative? And we just look for the sign on the slope, right? The slope is positive, therefore the correlation has got to be positive. So just look at your slope, your 2.7469, that is positive, therefore our correlation or coefficient, correlation coefficient r is positive as well. All right, so this is kind of a mathy problem, but they always give you this problem on the in the AP test. You know that you're guaranteed you're going to have a problem like this on the AP test. It always is there, generally, often in the multiple choice section, but it's almost always there. So there's a relationship between a bunch of different things here. So if we're trying to write the least squares regression line, in order to write the equation of the least squares regression line, you need A and you need B. All right, we can find A and B using, our calculator will spit it out to us if we have the data, but we can also find it if we know the standard deviation, S sub y, the standard deviation of the response variable, if we know the standard deviation of the x or explanatory variable, so response variable and explanatory variable, if we know their standard deviations and we know the correlation coefficient, r, then if we do a ratio times r, that will be equal to b, the slope of our best fit line. All right, and then once we have b, if we also know the x bar and the y bar, we can plug them into this equation, and that gives us our a or our y-intercept. So I think there's probably one homework problem tonight where it gives you the x bar, the mean of the explanatory variable, gives you y bar, the mean of the response variable. It also gives you the standard deviation of each, and it also gives us our correlation coefficient r. So when you know those 5 things, you have to find b first, then you take b, plug it into this equation, and you can get a. So be on the lookout. There is, I believe, a homework problem using those formulas in the homework tonight. Okay, correlation and regression are powerful tools for describing the relationship between 2 variables. When you use these tools, beware of some of the limitations. All right. There is a distinction between the explanatory and response variable. So that distinction is pretty important in regression. So for example, in the F-150, if we used miles to predict the price, then we have one equation, and that equation is listed up here. Okay, look at what the S is and what the R squared is. All right, then what if we had done it in the reverse? What if we had used the price to predict how many miles were on it? Okay, notice that the equation's very different. All right, they're both negative slopes in this case, but notice that the equations are very different. The y-intercept is different, the slope is different. Also notice that the S, standard deviation of the residuals, is different, right? I mean, the number, I mean, here we're talking about miles, and here we're talking about dollars, so it makes sense that the standard deviation of the residuals would be totally different. Now, maybe surprising, maybe not, the R squared, or the coefficient of determination, is the same in each case. And really that shouldn't be surprising, because you remember back when we talked about correlation, correlation is independent of which variable you use as the response and which one you use the explanatory. So if we should know that if we use miles to predict price, we get a certain correlation. We would get the same correlation if we use price to predict miles. So the correlation's the same. It makes sense that the R squared coefficient of determination should be the same, because it's just R squared. So if R is the same, R squared would be the same. So that shouldn't be surprising. But the equations you get and the standard deviation of the residuals, because the residuals are going to be way different, right? Those change. So just be careful. It does depend on which one is the explanatory and which one is the response. All right, so pause this video, and take a minute and try to decide which one of these scatter plots, which one has the highest correlation R. So start from high to low. Which one has the highest? Which one has the lowest? Pause the video, just try it, and then I'll reveal the answer. Okay, it's sort of surprising, probably, that actually the correlations are all the same with these. Now, they picked very specific points, right? It's not, you can't just pick 4 general scatter plots and expect them to be the same. So the whole point of this is that for some of these, a linear model doesn't even make sense. But it's only for if we were dealing with linear models. So for example, this one here, I mean, it doesn't even make sense to plot a line to this, because it's clearly curved data, right? This one probably as well probably doesn't make sense, right? All the data is sort of, vertically there. So it doesn't really make sense for probably these two to even think about calculating a correlation or trying to find a best fit line, because a line is probably not appropriate. Here, yes, this one would be okay. There's one way up there, right? And this one seems to be fairly linear as well. So just because you can run a correlation, you really want to look and see if the graph makes any sense, right? So it only makes sense to really do it. And what's great is if you actually, for these 4 examples, if you actually ran a best fit line, right, threw that data into your calculator and asked for a best fit line, in each case, you would have the exact same line. But again, doesn't really make sense to look a best fit line for this one, or certainly for this one, because it's clearly curved data. So just because your calculator will give you a correlation doesn't mean that it's appropriate. So be careful. All right, correlation and least squares regression lines are not resistant. They change dramatically depending on outliers. All right, so this one, you can see you have a bunch of data. There are 2 points that are quite different than the rest of this data, and that's this child up here. So this is the age at which the first word, the age in months of the first that the child was when they said their first word, and then actually a score, a test later on, right? So a score on a test. So they're saying, can the age in months of when the child said their first word, can that be used to predict the score? So if they were much younger when they said their first word, seems like they have a higher score. And then generally, if they take much longer before they say their first word, then their score is a little bit lower. So it kind of makes sense that this would have a negative slope to it. But what the point of this is we want to look at, like, if we took out the child 18, and if we took out the child 19, how would this affect the lines? And so we want to talk about influential points, but also sort of outliers as well. All right. And so outliers here are very different than when we were talking about outliers with one variable, right? So the 1.5 IQR is a way of finding an outlier, but you can't use that here because we're dealing with two different variables. We're not dealing with a box plot. We're dealing with a scatter plot. So you can't really just use a 1.5 IQR. It doesn't make sense here. And so what we want to think about is if we remove a point or add a point, does that influence the correlation? Does it influence or change the least squares regression line? So here we can see, if we use all 19 children, what the slope of the line is and what the correlation is. All right, so the correlation is moderately strong at 0.64. So that's moderately strong. It's negative, of course. And so that's the green line. That's with all 19 children in. All right. So what if we took out this child here, this child 19? If that took that out, then what happens to the correlation? The correlation gets stronger, right? Because the data is now more linear. Okay. The curve also changes a little bit. This 18 pulls it down sort of closer to it. Okay. It's a little bit further away from the 19 and getting closer to the 18. All right. And then if we leave 19 in but take 18 out, then you can see this is the pivot point here of the lines, and it pulls this line up a little bit from the green to the blue. It pulls it up. Also notice the correlation gets worse. Right now it's just super weak, right? It's moderate, close to being fairly strong. Now it's just obliterated. Without 18 is very influential. Without 18, the correlation really goes bad. The very low linear relationship, the strength of the linear relationship is really weak. We're going to look at another kind of simpler example. I think this one's a little bit tough. There's too many things going on this screen. It's kind of hard to see. I'm going to look at a simpler example in a minute. Okay, so we're talking about influential points. So least squares, the least squares line makes the sum of the squares of the vertical distances to the points as small as possible. So that's taking the square of the residuals and making them as small as possible. So a point that is extreme in the x direction with no other points near it pulls the line towards itself. So that means when a point is far from the rest of the points in the x direction, so it has an explanatory variable that's far above or far below our data, it tends to pull the line towards it, okay? And that would be considered an influential point. So an outlier is an observation that lies outside the overall pattern of the other observations. Again, we don't have any kind of formula to determine whether it's an outlier or not. We just have to say it's outside the pattern of the other observations. Points that are outliers in the y direction, but not the x direction of the scatter plot, have large residuals. Other outliers may not have large residuals. So outliers are things that are outside the pattern of the other data, and sometimes they can generate really large residuals, and those large residuals are going to typically decrease our correlation. All right, observation is influential These are kind of related ideas, this outlier and influential. So an observation is influential for a statistical calculation if removing it makes markedly change the results of the calculation. So points that are outliers in the x direction of a scatter plot are often influential for the least squares regression line. Okay, so let's look at a sort of a simpler example. All right, so I just made some points. You'll see the link that you can use to play around with this yourself. But I made some points. I don't know how many. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 13 or 14. I don't know if I count that one. So 13 or 14 points. And you see the correlation is 0.86. And I also included the best fit line there. Okay, what if we added a point? So this point, these are both sort of outliers, right? They both will influence, right? So this is an outlier sort of not in the x direction, but in the y direction. This one kind of falls in the pattern, but it's still sort of outside. This one's going to pull the point towards it, pull the line towards it. This one's also going to pull the line towards it. So think about where this line is, and let's start with this one up here. If I add this point, what do you think is going to happen to this regression, and what will happen to this line? So you can see here that I have, this is how if you click on this, you have to go to the electronic version of the PDF, obviously, and you can click on this and it will take you to the little applet that comes with our textbook that I used to create this. So you can play around with this idea yourself. So you can see this point up here pulls the line up towards it. This line moved up a little bit, right? You can see with the sort of the y-intercept here, it went up some. It also ruined the correlation, right? It was fairly strong here. This is fairly weak, okay? So an outlier in the y direction, but not in the x direction, will often create a huge residual. And remember, residual squares are what we're trying to minimize. And so that just ruins the strength of the linear relationship. So now let's go back and forget about this point and go back to these, and let's add a point out here. So that point is out here somewhere, sort of following in line with this best fit line. And you can see that strengthens the linear relationship, okay? I mean, it was already pretty high, but it's even got stronger because that strengthens the linear relationship. This point up here does not. It weakens the linear relationship. This one strengthens it. And so it's increasing the R value. And again, click on this link here in the electronic PDF if you want to be taken to, go to the little applet that allows you to play around with that if you want to investigate more. All right, so this is the homework. There is one problem that requires a 4-step. So remember, you're gonna restate the question that you're trying to answer. Say in your plan what you're going to do. You're going to make a scatter plot. You're going to make a residual plot. What kind of graph are you going to do to answer the question in number 1? Okay. Part 3, you'll actually do that. Create the scatter plot. Throw the data in, whatever. Create a scatter plot or whatever it is that you're going to do. Maybe it's a residual plot. We'll have to, see. Maybe in the plan you said you're going to look at the correlation, or maybe you're going to look at the coefficient of determination. Whatever it is that you're going to look at, you'll do that in 3, and then you'll answer the question in the conclusion. All right? So this homework is due next class.